No, na to, aby sme videli, ako teória grafov súvisí so všetkým týmto ostatným. Toto je jasné, že it's pretty obvious that in number theory we have these different number fields. It's pretty obvious that differential geometry deals with a lot of spaces where projective spaces are one of the types, and of course we construct projective spaces from all possible number fields that we have here. Then there's group theory, which deals with symmetries and groups, which are the ultimate tool to describe symmetries. And then there's a structure underneath every group that's called the algebra. And this is the classification of all the semi-simple Lie algebras, which are pretty much the most reasonable ones in physics and the only ones that are being encountered and used in physics. Now, given a certain algebra, an algebra is fully defined by something that's called the Cartan matrix. So it's a matrix, let's say a 2x2 matrix, that has two 2's on the diagonal, and something else over here. And this is something that one has to know more about the structure theory of Lie algebras, and in order to know what the Cartan matrix is. And but it's one of the tools that can shed light on the very structure of these algebras and stuff like that. Now we can compute a dimension of an algebra. We can compute its irreducible representations. Representation is a form of realization of the algebra. So if I say I have a SU2 algebra, it's usually denoted with lowercase letters. Now this is this object with two nodes. But then I can create a representation of that algebra, which is when I actually write a matrix that has 2x2 matrix that has entries Z1, Z2, Z3, Z4, and obeys all the requirements that this algebra has. Now this is a concrete representation of this algebra. Now representation can be reducible or irreducible. So very intuitively, if a representation is reducible, let's say let's say I have a matrix, X, Y, Z, W. And if this is a reducible representation, I can write it as a direct sum denoted like this, of some smaller representations. So let's say I take this diagonal representation of this algebra, so this would just be x00w, and this is a representation by itself. And then I take the rest, so I take yz0. So I took this reducible representation and reduced it down into its two irreducible modules or components. Now it's very crucial in a systematic study of these algebras to know exactly what the irreducible representations are, which representation is reducible, and so on. Because every node in Dynkin classification of algebras corresponds to a certain irreducible representation of the algebra. So if I take this node and assign 1 to it, I'm gonna have the fundamental or the vector representation of the algebra. So let's not talk about AN. Let's talk about SO3. So BN series SO3. So we know we have a vector in three-dimensional space. So X, Y, Z. We have a vector V. And the fundamental or the vector representation would be the one that I've described in the previous video. So it's like, imagine you have a vector and now you're applying a matrix to it which rotates the vector in the three-dimensional space, keeping its length constant. That would be the vector representation of SO3. So the matrix is of the form, imagine I would fix the Z dimension, so it would be 0, 0, 1, 0, 0. So that I wouldn't rotate it in the Z, I would only rotate it in the XY plane. So that would leave me cosine theta, sine theta, minus sine theta, cosine theta. So this would be the form of the matrix of the vector representation of SO3. Now we have fundamental or vector representations of all the other algebras. We use, say, SO4 or SO2. SO2 would just be this. Then SU, whatever, But my point is someplace else. I wanted to present you the last link between this field, this fields, and the field of graph theory. So graph theory deals with, for example, polytopes or some other shapes. And now, for this algebra, I said that Cartan matrix is something that fully describes the algebra. Now, the algebra is fully described as well by something that's called its roots. So, a simple algebra may just have one root, but complicated algebra might have 2 or 3 or more. Now, let's denote the root vectors by alpha and beta for some algebra. Now, let me present you the G2. So this exceptional algebra of G2. It has 2 roots, alpha and beta. They are not the same length, whereas some simple algebras have 2 roots which are the same length. These are not the same length. So the length of alpha does not equal the length of beta. Now there's an angle in between them. So in this case it would probably be, I can write alpha here and then beta here, where beta is longer and the angle is, let's say, 120 degrees. Now I have this. I construct some more vectors out of these two. Okay, let's say I just add up these 2 vectors. I get another one. Now I make 2 alpha plus 1 beta, so I get 2 alpha, 1 beta. So I get a vector here. Now I get 3 alpha plus beta, or plus 2 beta, so I get something like this. And then I create a certain number of these vectors. And then there's a thing called the Weyl group, which is usually denoted by W. And Weyl group is usually a discrete group that I apply to this configuration, and it just gives me the image over here, the image over here. So in this case, the Weyl group would be S3, because this is 120 degrees. So I need one more like that, and I would reconstruct the configuration, and then one more. And I would create something that's called the root system of this algebra G2. It's called the root system. So these 2 roots are called the fundamental roots. It's only 2 of them. So this algebra is fully characterized by knowing the number of fundamental roots, knowing their relative lengths, and knowing the angle in between the roots. And then there might be something about which combinations, linear combinations of these two roots I can create in between them. But then, as soon as I know that, the algebra is fully defined. And I just apply the Weyl group, which is S3 in this case, to create the full root system. And the root system is something completely fundamental, describing the algebra at hand. And now, let me tell you the connection in between group theory, differential geometry, number theory, and graph theory. So, if one considers, let me give you the most extreme example in order to illustrate the boldness of this connection. Take E8, which is the biggest exceptional algebra. If we were to draw its root system, it would be very complicated. In fact, it would have 240 vertices. So it would be it would be a very complex structure, and it wouldn't just be two-dimensional like this. It would be 8-dimensional, in fact. One could look up on the internet that the root system of E8 is a 4-to-1 polytope, which is the biggest finite shape, semi-regular shape that was discovered by Euler, Bernhard Euler, back in 1854. And this 4-to-1 polytope at the same time is as if we would draw the first 240 octonions that are smaller in length than some octonion. So if we were to draw the first, all the complex numbers that are smaller than 1, so we would have a Gauss plane, and we would draw a unit circle, and everything in here, which would be, infinitely many points in here, smaller than 1 would be all the complex numbers that are smaller than 1 in norm. So their norm would be smaller than 1. Now, if we take octonions, let's denote them by O. And we write all the octonions that are smaller than a certain octonion. It would be 8-dimensional drawing. This would be 4-dimensional, this 8-dimensional, this 2-dimensional, this 1-dimensional. And it would be 8-dimensional drawing, and what we would draw, it's like they would be here. It's only 240 of them. And it would be the same, it would be 4-to-1 polytope, and it would be the same as the root space of E8 algebra. So this incredible connection is something that's bothering me. And the idea at hand is to create an expert system that would give us more insight on what's going on right here. Because I believe that no matter which field of mathematics one likes the best, if we put on the right glasses and we look through one of the fields, we might be able to see something that's over here. It's like a melting pot. You know, number theory goes here. Group theory originates from here. Then there's differential geometry that originates from here. And then there's group theory that originates from here. And our idea is to have the right glasses to look through. And which part of mathematics is the most beautiful of these? Well, hard to tell. For me, I'm a theoretical physicist. Group theory is the most beautiful one. So I want to look through group theory, and I want to see. I want to explore something over here that might give us a lot of insight on these other fields as well, and in fact might serve as a language in understanding the connection in between these fields. Now, differential geometry is sort of a utilitarian field, which just, you know, treat everything to be smooth and just, you know, just allows us to describe smooth structure spaces. Now, graph theory is a way of depicting it all, and is a way for a computer to see, you know, how the different shapes, you know, look like, or what they share in common, or what the patterns are over there. So this is a good way for a computer. This is just utilitarian, so whatever. Now this is something that a mathematician would do, but you know, having the apparatus of group theory, we can learn a lot about what's going on down here. Now, the idea is as follows. You know, as a physicist, I believe that world is nothing but some manifestation of symmetry. You know, the standard model of particles that we have. It's nothing but just SU3 cross SU2 cross U1. So these are all semi-simple Lie groups or algebras, whatever. Now this is electromagnetism. This accounts for weak interactions. So, okay, let's say weak. Now these two together, let's call them electroweak theory. By the way, written down by Abd Salam at Imperial College a few decades ago. And now this is a strong nuclear force. Now this together gives us the description of all the 3 out of 4 fundamental forces. Now the present day theorists, they look for a unified theory of everything. So we want to have gravity in our theory. We want to have a quantum description of gravity, and we want to have a theory that would probe and describe all the particles that we need. So there are problems with, you know, dark matter, for example, because dark matter is sort of gravitating matter that we don't see. You know, we observe a galaxy, and within it there's stars, you know, planets, and then there's a star here, you know, very far from the center of the galaxy. And now we know the matter distribution over here. So let's, all right, some rho, whatever. So we know matter distribution. And we know how fast and at which orbit this planet should be orbiting the system. We know that. But the observation implies that there's something wrong. Because this is way closer. This star is way closer and is orbiting way faster. And now, the only explanation for this is that there's more matter in here. There's more matter in here that we can't see, that causes this planet to be gravitationally more attracted here. So orbiting at a lesser radius and at greater speed. The explanation? Dark matter. Also, the universe, cosmology of the universe that we inhabit. So, at a time, let's call it 0, there was something like a Big Bang, which is pretty well theoretically gaspered, and so there was a huge exponential inflation of the universe. It's not clear how this went on, because but then suddenly the universe slowed down at a point at which it wasn't expanding, and we would think that it would just now the gravity takes over, and it would just so everything would be attracted together, and now the universe, upon expanding like that, would just start crushing down, and would just getting smaller in size, and eventually would end up with a big crunch. But other is true that at this point the universe started expanding exponentially again, and so the explanation for this is dark energy. So something that somehow causes a negative pressure in the universe that just keeps, creating space in between galaxies and just causes the whole universe to expand again. And now, we need a particle for dark matter, We need a rigorous and experimentally tested explanation for dark matter. So over here we're looking for a sort of particle that we don't yet have. And here we're also either looking for a new particle or something else. And all of this has a chance to be tackled by the tools and means of the string theory. Now, string theory, there's no string theory that is consistent unless it has a supersymmetry in it. Supersymmetry, a new type of symmetry of the world that pretty much takes all the particles that we have in the standard model. So let me summarize it right here. So in the standard model, we have quarks, right? Top quark, bottom quark, charm quark, strange quark. Sorry. Up quark, down quark, charm quark, strange quark, top quark, bottom quark. Then we have leptons. So we have electron, muon, and tau. We have electron neutrino, muon neutrino, and a tau neutrino. Then we have bosons, which are particles that mediate forces. So electromagnetic force is mediated by photons. Strong nuclear force, so the force that holds two up quarks and a down quark together to create a proton, those are gluons. And then we have W plus minus and Z boson. On top of that, due to renormalization and due to the fact that we need mass for every particle in the spectrum, we have a Higgs boson. Now this is the standard model. Supersymmetry is a new type of symmetry that takes a particle and says that we have a different particle called a superpartner for that particular particle, which is the same in every aspect except for every fermion we have a superpartner that is a boson. So, fermions are, for example, electron, you know. So, if you have a hydrogen atom, you have a proton in here, and then you put an electron here. And then you put another one, and it can still be on the first energetic level. So there's another electron. Why? Because this one has spin up, this one has spin down. But there's no scenario in which fermions can occupy the same quantum state. You know, the quantum state of this electron is determined by the energy level, which is denoted by n. Then the orbital momentum, which is denoted by L. Then the momentum in the z direction, which is denoted by m. And that's it. But there's one more thing, and that's the spin. So we have 4 quantum numbers that determine. Now, if we were to add a third electron, it wouldn't be on this layer, but it would be, you know, it would be here. Because then 2 of them would have to be completely the same or in the same quantum state, which is not allowed by the Pauli exclusion principle. So no. Now supersymmetry takes all the particles we have, and for every fermion creates a boson, and for every boson creates a fermion. And that's where we have so n equals 1 supersymmetry, which is also called a minimal supersymmetry, which just give us twice the number of these particles. So it would give us another, 4 times 4, 17, another 17 particles. So for Higgs we did Higgsino, or Higgsino for electron, we would have selectron. For up quark, you know, we just have super partners for these. And now there's a space for particles that can be the particles of dark matter. You know, there's a space for the particles that can cause the effect of dark energy. You know, that's why supersymmetry is very much appreciated in nowadays science. So the reason I thought I'm talking about supersymmetry is because I just want to stress out the role of symmetries in physics and in the overall understanding of today's world. So that's another reason why studying, or the study of symmetries, is a very fruitful one indeed. So, what can be done in this matter? Well, how about we start by putting together 2 very useful fields of science nowadays. How about we take artificial intelligence? How about we take expert systems and we feed them with group theory? Now, I don't want this system to be computing root systems of algebras in the way that I could do it on the paper, or you know, every standard program to do that. Given the axioms, given the formulas, how to compute the root systems, you know, every program can do that. What I want to do is I think I want somebody to develop an expert system that's gonna learn how to do the classifications of Lie algebras, how to draw the root systems. So for example, for a n series, n going from 1 to 10, you know? Let's say these are my axes or whatever. So we just draw the first root system, which is like one root, and then Weil group is S2, so we just invert it. Now, and S2 would probably be something like this, so it would just, now S3 maybe would have another one. And now S4 maybe would add us something, you know, add us two other positive roots, you know. Then maybe S5 would just give us something more complicated, you know. Then B series would give us some other thing, you know. Maybe something here, maybe here, and then maybe two longer, you know, add vectors. And all of these would give us different pictures. And what I want to do ultimately is I want to have an expert system that not only knows how to calculate this, you know, in the hard way, in the tedious way, but I wanted to look for patterns in these, and I wanted to learn the ultimate patterns on how to create these images. And ultimately, I want the thing to be able to take all the symmetries, all the reasonable symmetries that there are. So take all the AN series, take all the BN series, take all the CN series, take all the DN series, take all the exceptionals, and I wanted to be able to draw the spectrum, you know, of all the root systems on one picture. It's going to be more than two-dimensional, obviously. And I wanted to be able to play with it. So if we would just have purely A series, what does it give us? If we allow all the products of AN series algebra, so we would allow to draw a root system of SU5, you know, times SU10. Like, how would that look? How would that look? And then ultimately, it would be very interesting to see something that I invented a term for. I called it the hypersymmetry. So I want to see how does a hypersymmetry looks like. So the key point here is the symmetry of all symmetries. I want to see something like this. And I want the expert system to get better in this. Better than people are, you know? Because we can exploit a lot of the features of the expert system in order to do this. And then we can have we can maybe simulate different scenarios of symmetry breaking. Because what is actually the case in our universe is that we have some symmetry at higher energies, and as we go down with energies, as the universe expands, the symmetry breaks. And it breaks down to some symmetry, some smaller symmetry, times some other smaller symmetry. And now this, for example, in the spontaneous symmetry break, and this is the Higgs mechanism right here. And since Higgs mechanism was observed and confirmed, and it works pretty good, I believe that, this is very philosophical, but maybe this world, as string theory, suggests that we have 11 dimensions, and one is time, 10 is spatial, and then as the universe expanded, only 3 of them expanded, and the rest remained compactified, doing something that's called Calabi-Yau manifold at every time-space point. But I think that there's something like a hypersymmetry that breaks down into smaller symmetry, and maybe then again breaks down into some smaller symmetry, and eventually breaks down even more. Maybe somewhere in this process, a gravity is just breaking out of the thing, and ultimately what we have here is SO3 times SU2 cross U1. So I think this is a very fruitful way of thinking about the whole thing. And so it's going to be very hard to formulate this problem rigorously, but I think if anything has to be done, or if anything's worth to be pondered upon, this would be one of those things. So yeah.